I think it's working. Okay. So yeah, we got tomorrow will just be a work day. I've kind of covered every type of problem. If you guys need to see another example, I guess we can do that. But so covered every type of question you might encounter, except for we have not done the oil rig problem. That's the last page. I'll cover one of those today. I figured maybe one more example of maximizing a rectangle under a curve. That's kind of another like commonly encountered question that you might see in calculus. So let's just do 28, I guess.
Okay.
So basically the problem says you've got this curve. This is the curve y equals square root of x. And then you've got the line, well, it just says the point tends 0. So this right here is the point tends 0. And it just says, okay, assuming you have a rectangle that has to have, this is its bottom right point, and some point along this curve, so this is some point x, y. If we've got our rectangle inscribed inside that, what is the biggest possible rectangle you can get? Now, again, obviously, or I think it's kind of obvious that you can make this rectangle as small as you want. If you just choose this point to be like really close up here, do you see how that would be like? You can make it as skinny as you want, or you can put the point way down here, and the rectangle would be as short as you want. So obviously, again, the area can approach 0. You can make the area. What's going on out there?
They heard my Julius Caesar joke.
They heard your Julius Caesar joke, exactly. Okay, so anyway, so clearly the only optimization you can do is to maximize it. So what's the biggest you can make of that? Okay, so first thing, step 1. It's basically a 3-step process. Every single question is a 3-step process. Write the constraint, identify the quantity you're trying to optimize, and then 3 is just do all the calculation. Okay. So step 1, constraint.
Yay.
The constraint is you're going to pick an xy point, but the y value of your point has to be equal to the square root of your x value. So if you pick an x value of 4, then your y value has to be 2, for example. So that's our constraint. Or at least that's part of our constraint. The other constraint is that our x value has to be between what 2 numbers? 0 and 10. So there you go. We got 2 constraints. Our x value has to be between 0 and 10, and then our y value we pick has to be equal to the square root of our x value. What's the quantity we're trying to optimize?
10 minus
It says times y.
There you go.
Boom. Yay.
So if you can jump straight to that, great. Then, so the area of this, so this distance right here is x. So that distance there would be, what's the base of the shape? N minus x. And what's the height?
Y.
The y value, which of course is the square root. So you can sometimes just jump straight to the area is n minus x multiplied by y, but a quick substitution will get us the thing we're concerned with. So after the substitution, so step 1, constraint. Step 2, identify the quantity you're trying to optimize. Step 3 is all the algebra calculation stuff. So the first step of that calculation stuff is the substitution. So you've got replace that y with square root of x. Let's just stop here. Does anyone have any questions on step 1, step 2, or step 3? Yes?
So for step 3, like, is the root of x, is that because of the y, like what that equals?
Yeah, so we replaced this y with square root of x because our constraint said that our y value is equal to the square root of x. So your substitution will pretty much always be referencing the constraint. You guys back there got questions or? No?
Does it like always reference the constraint or is it basically?
Pretty much. Yeah, because, well, I mean, do you see how we might have been able to get away with just writing this height of the rectangle as square root of x and just going directly to this?
Yeah.
Does everyone see that? That is certainly viable, but typically it's the more complicated the problem, a lot of times the easier it is to write it like this and then do the substitution. I'm sure there's no, that's a good question. Any other questions on this, on those 3 steps? Okay, so this is the quantity we want to optimize. What's the biggest this number can possibly be?
Oh, sorry.
Oh, there's the answer 10?
No, I'm sorry.
Oh.
I thought you were talking about the X value.
Yeah, that's what I thought too.
X. I was just saying, you could throw out a couple possibilities, like, I don't know, some easy ones would be, let's say X was 4. If X was 4, you'd have 6 times 2 is 12. So, I mean, the area could be 12. I don't know, if X was 6, you'd have 4 times root 6, which is a bit harder. I mean, it's not bigger than 12, I'm not sure. You don't think it is, but. Anyway, so time to say, well, let me graph this real quick. Does it make sense how if X is 0 or if X is 10, the area is going to be 0? So there's some sort of Humpty Dumpty in there that's happening. So if I plug in 10, I get 0. If I plug in 0, I get 0. So the question is, when does this function have a derivative of 0? When is the derivative going to be 0? So to take the derivative of this, it's probably best to take one extra step and simplify it first. So 10 times root x. And then what do you guys think x times root x is? X to the, you could write it as x root x. X to the 3 halves is going to be a lot easier to deal with. We all get why that is that? Okay. So ready to take the derivative then. Okay. Derivative of 10 root x. Okay. Derivative of this would be 3 halves. What do you get? You get 3 halves times what? Times root x, right? We okay with that? Then what do we do? So that's a formula for the derivative of this curve. Yeah, we want to know when does it hit the top? The top happens when the derivative, so this top happens when the derivative is 0, when the slope of this tangent line is 0. So next you set it equal to 0.
I have my answer.
Okay. Now the algebra here is, it's not too bad because you can kind of see what's going to happen with the x's, right?
Yeah.
So you have 5 over root x equals 3 root x over 2. If you like that cross multiplication idea, then great. However you want to think about this. I mean, you get 10 thirds. Because root x times root x makes x. 2 times 5 makes 10. Divide by 3. Okay, so there's our x value. What's the y value?
Just go back and number the square root of 10.
The square root of 10 thirds. Very good. Kind of a weird number, right? Now, does the question say, it says find the maximum possible area. So do you see a spot on the board where we just, I mean, I guess we could get this, we did get the y value, but where could I just plug this x value in to get my answer? The area formula. It's asking what is the biggest area? Well, that is the x value that corresponds to that happening, so plug it in. So let's do this in blue, I guess. Okay, so plugging that in, 10 minus 10 thirds times the square root. 10 thirds, is this still visible? Okay, yeah, it's still on screen here.
20 thirds.
Kind of a strange number, right?
That's a weird.
Don't think anyone predicted that one, pretty sure.
20 thirds.
Wow, very intuitive.
Very intuitive. So,
You would like that?
yeah, I mean, we could write it, we could multiply this by root 3 over root 3 and get, you'd get what, 20 times root 30 over 9? Does that number look that much? I don't know.
No, it doesn't,
I don't see a
but-
huge difference. But there you go, that's the answer. The answer is this very bizarre number. 20 thirds multiplied by the square root of 10 thirds. So kind of weird, right?
Yes.
There you go. So let's back up. I guess, were there any questions on those last like 2 steps?
So the answer is like what x number equals and then also the 20 versus 3 over 9. What those 3 things?
Well, the way the question's phrased, so suppose the question had said, what are the dimensions of the rectangle of the maximum area? Then the answer would be, well, that rectangle has a base of 20 thirds and a height of root 10 thirds. But the question is phrased, what is the max, or find the maximum possible area? So that would imply that you got to plug your values into the area formula to get this. This right here would be the maximum area. Does that make sense? So it's all context dependent, like everything else. Like everything is in life, right? It's like they might have just asked on your quiz. I think a lot of times the question will be asked like, what is the choice of x value that maximizes the rectangle? In that case, the answer will be what? 10 thirds. Or you could phrase the question as, what is the height of the largest rectangle? Okay, well, if that was the question, then there's the answer. It's pretty standard though to be asked, what is the actual biggest, what is the area? Any other questions? Doing good?
Yeah.
All right, we're gonna do the famous oil rig problem. So Jesse's favorite.
Yeah.
What kind of oil do you use?
What kind of oil?
Oil, or what kind of oil?
There's so many pencil marks
Oily
on
type.
Do they have a bike?
They have bike rack. Yes.
We're gonna do the Oilers problem.
Good.
Good one.
Yeah, we're about to lose your spot.
Okay, so if anyone was paying attention during the dog thing I mentioned, and this is kind of analogous to that. The dog trying to minimize the energy he spends, which is analogous to light minimizing its path through 2 media. So if you read the question, I hope I've stated the question clearly enough, which is that there's water and there's land. Okay. So here's water. This is water. of land. Okay. Now, again, these numbers are made up, so don't.
That's a lot. I mean,
I bet it would be a way more than that.
I know,
I also bet
still.
building in the water would cost like way, way, way more than building on land. But I picked these numbers because it ends up making the solution kind of easy to visualize. It's just the general principle. So there's an oil rig here. If you don't like oil, you can imagine it's anything else. This could be a vegan tofu production facility. And then here is the Whole Foods that you have to transfer it to. Okay.
I'm hungry right now. Tofu sounds so good.
Absolutely.
What?
And you're gonna pipe it.
Yeah, we gotta have that pipeline. It's asparagus water, actually. The asparagus.
Naturally cooling it by sending it through the ocean. You're naturally cooling it. Well, it's a natural
Okay.
It's very complicated.
This is 5 miles, and this is 10 miles. And we need to get the oil from the oil rig from point A, or the asparagus water, the avocado toast, whatever you want it to be. We need to get that to this point. We want to obviously minimize the cost, right? If we wanted to maximize the cost, I just have the pipeline run all the way over here and just build a whole bunch of unnecessary pipe that costs me billions of dollars, and great, we bankrupt the company. So-
Let's go.
So let's think about the two obvious solutions. So you say, well, it's more expensive to build in the water, to build pipe in the water, and it's cheaper to build on land. So you might go, well, it would make sense to just then minimize the amount of pipeline in the water then. Just build straight to the land and then build over. Does that make sense? So that is a possible solution. It would be 5 times 5 million plus 10 times 3 million, because the pipe on land. It is using more overall for sure. Or you might go, let's just minimize the distance then. Let's just go straight from the oil rig to the facility, right? That would minimize the distance, but you're spending an awful lot of time in the water, right? So what we're going to show is that there's actually an optimum path where what you do is you pick some point and you go there. It's kind of like the dog problem, the dog going to his bone in the water. Our path is actually going to look something like this. How do we feel about that? Does that make some kind of sense?
Yeah.
Okay. So I'm going to put a little symbol here to represent the fact that we're choosing this point. So I'm going to call this, well, what I'm going to do really is call this distance x. So how big is this distance?
Why?
10 minus x. You could call it y, and then set up your constraint and then do a substitution for sure. This is one of those cases where I think it makes more sense just to like label it x and 10 minus x. It's always, it's always up for debate how you want to set it. Okay, so what are the two distances I'm working with? I already kind of got that distance, right? I know. Yes, Aiden.
So how would you go about getting that shape if you didn't if it didn't just come to you off the top of your head? That
Get what
kind
shape?
of idea of instead of going straight down and over that, and instead of coming down a little bit more angled.
Well, so okay, the logical process would be something like that's a great question. I mean, so we can calculate it really fast, right? Did we say it was 25 million? So 5 times 5, and then here would have been 10 times 3. So it's 55 million to do it that way. And then you might have gone, well, what if I go direct? This would be what, the square root of 125 times 5 million. Maybe use a calculator to tell you how big. Well, I mean, I know that number is going to be rough, just under 13. 13 times 5 is 65. So I know that's a little bit too big. Okay. And then you might go, well, what are the alternatives? I mean,
the guy in the video said you want the 120-degree angle.
It's true.
I don't think it ends up being 120. I could be, maybe it is. I don't think so.
The angle from A to
Because
B.
that was under a very special, well, in the Steiner tree problem, all the roads have different weights. You can modify the Steiner problem and say, you could say, oh, I've got these 4 towns. I want to connect them. And the solution ends up being a Steiner tree. But if you put like a swamp here and say, oh, it's really expensive to build over the swamp, then that's going to change the ideal configuration. So there's a whole branch, well, a whole field of like computer science problems where you have like a network. I believe if you could somehow figure out the ultimate solution to this, you'd be famous. But say you have a bunch of cities, it's called the traveling sales